Using electronic control over gear selection and shifting in an automatic transmission, vehicle manufacturers have been able to deliver significant improvements to vehicle efficiency, emissions, and the overall driving experience. ECM-controlled auto transmissions function in a similar way to older hydromechanical types. However, instead of relying on governor speed and accelerator pedal position, they use software programs and a mechatronic unit to determine and perform each shift point. Not only are these newer transmissions more reliable, they require significantly less maintenance over their service life. For any of us that have repaired a typical hydromechanical transmission, we know that there are cables, rods and linkages that need to be carefully marked and tucked out of the way before disassembly can take place. If we need to remove an ECM-controlled transmission for repair, it is often just a case of disconnecting a harness, instead of the cables and linkages of old. Externally, all automatic transmissions look similar, but internally they are very different. Modern electronic automatic transmissions do not use a mechanical governor or a throttle pressure measuring device to control fluid line pressure or operate the shuttle valves. Instead, a control module mounted to the valve body uses inputs from a variety of dedicated transmission sensors. Engine performance data and navigation data can also be accessed from the vehicle's onboard communication network. The control module processes this raw data and then selects an appropriate action to perform. Whether it's a simple upshift due to an increase in vehicle speed, or a rapid downshift commanded by the driver using the gear selector with sports mode active. Modern electronic control units offer the key benefit of adaptive learning. This simply means that they are able to adapt their behaviour based on the current mechanical condition of the engine and transmission, the vehicle operating conditions, and the habits of the driver. Transmissions utilising adaptive learning have a line pressure control system that compensates for the normal wear and tear that takes place over their service life. As components within the transmission wear or mechanical conditions change, the time required to apply a clutch or brake will also change. The transmission control module monitors input and output shaft speed to determine how much time a gear shift actually takes. If the shift time is too short, the driver will experience a harsh change, while a shift that takes too much time to complete is described as flaring. The control module will command an increase in line pressure to compensate for a slow or soft shift, and will decrease pressure for a harsh shift. The end result is a transmission that provides consistent quality shifting and improved reliability over its service life. Adaptive learning capabilities allow for changes in the engine's performance, and it may also learn shift timing and torque converter clutch engagement from the vehicle operating conditions and driver habits. If a serious transmission or engine problem occurs, the control module may command a limp or fail-safe mode, whereby engine torque is dramatically reduced and generally only third gear is available. This protection mode allows the driver to limp the vehicle to a repair centre for diagnosis. An innovative feature of most modern automatic transmissions is that gear selection is detected by an electronic position sensor. Most transmission manufacturers still use a physical lever for the driver to move. However, actual gear selection occurs by means of electric solenoid. ZF utilises a mechanical shift gate design as part of the electronic selector assembly, which allows the driver to select a gear using a conventional lever that slides over detents. This allows the driver to see and feel which gear the vehicle is in, again similar to traditional automatic transmissions. In actual fact, a non-contact sensor attached to the assembly detects the selected lever position and then converts the information to digital format. This signal is then sent via a high-speed CAN message to the transmission control module. Gear changes can also be performed in some vehicles using an operational mode known as Tiptronic. This mode is used by the driver to shift up or down gear ratios sequentially, without waiting for the control module to perform the change. This shift mode can be accessed by either moving the gear lever to one side of centre and either pushing the lever forward or backward to change gear ratios. Some vehicles have controls for Tiptronic mode mounted to the steering wheel, whereby shifting can take place without the driver removing their hands from the steering wheel. This shift mode does have limitations. For the sake of self-preservation, most transmissions will not allow a downshift if the vehicle speed is too high. Likewise, it will not allow an upshift if the vehicle speed is too low. Early electronic control systems had their module mounted external to the transmission, or they were integrated with the engine control module and referred to as a powertrain control unit. These days, most transmission manufacturers install the module within the transmission, usually affixed to the valve body. We call the assembly a mechatronic unit. The valve body itself is similar to a conventional hydraulic transmission, and it still uses differential pressure acting on shuttle valves to control clutch apply and release servos. But this is where the similarities end. The mechatronic unit controls oil flow to and from the shuttle valves using shift solenoids. A 4-speed automatic transmission, like the 4L60E, may have up to 5 shift solenoids that are responsible for the operation of all gear ratios, both forward and reverse. The more gears an electronic automatic transmission has, the more shift solenoids are required. This ZF-HP valve body has 9 solenoids to service 8 forward and 1 reverse gear. Shift solenoids operate with spool valves to direct transmission fluid to the clutches, which in turn engage a drive gear. Let's take a look at this in a typical automatic transmission. When the transmission lever is placed in drive with the vehicle stationary, the ECM is programmed to select first gear. Fluid from the oil pump is delivered to one side of the shift valve via the manual and pressure control valves. This is the fluid that will eventually travel to the clutch packs. The solenoid and shift valve acts like a relay. When the ECM sends a control command to the first gear solenoid, a small amount of fluid travels from the pressure control valve past the solenoid pintle and onto the first gear shift valve. Fluid acting on the valve surface pushes the spool against the return spring, uncovering the fluid supply port. Automatic transmission fluid under pressure can now travel from the control valve to the first gear servo and clutch assembly, just like a conventional automatic transmission. As long as first gear is required, the solenoid remains activated by the transmission control module. When the module determines that the vehicle speed and load conditions permit second gear to be selected, the control module deactivates first gear solenoid. The solenoid pintle closes and fluid pressure from the control valve can no longer act on the spool. With a low pressure on the solenoid side, the return spring pushes the spool back to rest, covering the supply port. Trapped fluid below the spool is able to bleed back to the oil pan via the solenoid. When we look at the commands from the control module, we can see that they are in the form of a PWM voltage. Let's watch that again, but concentrate on the voltage at the solenoid. In the simple example we are looking at, when the shift valve is closed, the voltage at the solenoid is 0. To initiate the shift to first gear, a pulse width modulated voltage with a relatively low duty cycle is sent to the solenoid. This is gradually increased until the pintle opens, allowing fluid to press on the spool. Feedback to the control module from the output speed sensor confirms first gear is selected and drive is transmitted through the clutch and gear set. At this point, the vehicle speed should be great enough for second gear to be selected. The control module will begin to activate the second gear control solenoid by increasing its duty cycle voltage, while at the same time decreasing the PWM signal to the first gear solenoid. As a result, second gear will be selected while first is deselected. By controlling the duty cycle on both solenoids simultaneously, gear shifting is smooth and precise. By altering the operating speed and order of each solenoid within the mechatronic unit, The control module can perform all up and down shifts as required by the vehicle operating conditions. Modern electronic control transmissions are far more complex than their mechanical predecessors. With an understanding of how they operate, you may find them a little less intimidating. Thanks for watching.